Welcome to The Explainer. Today, we're unpacking something absolutely massive, how computation, mountains of data, and good old human curiosity have teamed up to completely rewrite the rules of modern science. If you've ever wondered how we went from researchers scribbling in dusty notebooks to global digital networks mapping the human genome, well, you're in exactly the right place. Let's get into it.
We're diving deep into Robert R. Cooper's fascinating book, The Thinking Machine Age. Throughout this explainer, we're going to dismantle that classic myth of the lone genius toiling away in an isolated lab. Because what Cooper reveals is a profound, real-world shift. Knowledge isn't built in silos anymore, it's a highly networked computational reality.
Okay, I want to start with a really powerful thought, straight from the text. Cooper writes that science was often delayed not because people lacked curiosity, but because the tools available to curiosity were limited. Think about that for a second. Our ancestors weren't any less intelligent than us. They just didn't have the machinery to process the sheer, mind-boggling complexity of the natural world.
So here's our roadmap for today. First, we'll look at how science hits the wall, then the thinking machine age, followed by data, the raw material, the danger of abundance, and finally, why the human element remains. Let's kick things off with Section 1, Science Hits the Wall, the limits of paper and patience.
You see, traditional science eventually hit a hard structural limit. In the older rhythm, discovery was literally bottlenecked by human bandwidth. I mean, a researcher could only read so many papers, run so many physical tests, or hold so many patterns in their head at one time, right? But this new engine, it runs on software and massive data abundance, tracking patterns on a scale that used to be completely unimaginable.
The big takeaway here is that science didn't just wake up one day and get super smart. It simply hit a physical and mental wall. The world's complexity literally outgrew what unaided human attention could handle. As researchers pushed deeper into complex living ecosystems or wild chemical reactions, it became super obvious. Human intelligence needed some serious structural reinforcement.
Which brings us to Section 2, the thinking machine age and the pivot to machinery.
So what happened when those older manual routines started breaking down? Well, they didn't just build slightly faster calculators. As the author points out, computers stopped being these passive support instruments just sitting at the edge of the desk. They became woven into the very fabric of how a hypothesis is tested. Today, they actually help create knowledge. They don't just document it. It's a total game changer.
And this creates a really fascinating chain of abstraction. We go from raw reality, stepping to a measurement, which then translates into data, gets fed into complex models, and finally spits out outputs. It's wild to think about. But today, scientists rarely interact with raw reality itself. The digital simulation is essentially standing in for the real-world phenomena.
Moving right along to Section 3, Data, the Raw Material, Mining the New Evidence.
Now, this brings us to the actual lifeblood of all these complex models, data. But here's the thing, data isn't some pure, untouched truth. It's much more like a manufactured raw material. Making it useful requires a ton of unglamorous, totally invisible labor. We're talking metadata standards, version control, endless data cleaning. The moment a researcher decides what counts as a broken record or what gets filtered out, they are actively shaping the conclusions of that study.
You can kind of think of metadata as the nutritional label for your dataset. Defining this metadata and cleaning it up, that's not just some administrative chore. It provides the provenance and the collection limits you absolutely need to give raw numbers actual context. Without that context, data is honestly incredibly dangerous. It can be misused or fed into models that treat completely different situations as if they were exactly the same.
And that perfectly sets up Section 4, the danger of abundance, the friction of scale.
Having massive mountains of this refined data actually introduces a highly deceptive problem. We've basically traded the old dangers of scarcity for the new dangers of abundance. Back in the day, you might miss a signal just because you lack data. But today, the danger is producing beautifully polished nonsense. Because outputs look clean, beautifully visualized, and mathematically confident, we can so easily confuse sheer scale with actual truth. And those outputs often become the flashy science headlines we see every single day.
This really forces us to wake up to the fact that just because we have fast algorithms, it definitely doesn't mean we have the truth. Scale can hide massive systemic errors. Cooper hits the nail on the head here, noting that a field capable of testing thousands of correlations will eventually find beautiful nonsense unless it builds norms strong enough to challenge its own outputs. When data is abundant, you're always going to find a pattern.
The real challenge is knowing if that pattern means anything at all in the real world.
Which leads us to our final stop, Section 5. The human element remains, the ultimate safeguard.
For all these incredible technological leaps, they absolutely do not replace the scientist. If anything, they make the human element more vital than ever. Because models cannot hold responsibility. They can't suffer the consequences of being wrong. Only humans can. The machine extends our reach, for sure, but it does not remove our responsibility. It can estimate, it can predict, but it definitely cannot decide what counts as acceptable uncertainty in, say, a life-or-death medical decision. And navigating this requires what Cooper calls disciplined curiosity. Honestly, it's the only thing keeping science from turning into an automated factory of polished illusions. Curiosity is what asks why the model behaved oddly. Discipline is what resists the temptation to just accept the first fast, neat answer a computer spits out. Put them together and they form the ultimate defense against technological complacency.
So, human judgment is actually becoming more important, not less. The burden on us now involves interrogating the model's assumptions, spotting biases in dataset labels, and, this is crucial, slowing down. In an age where literally everything is accelerating, knowing when to put the brakes on for rigorous validation, that is the true mark of scientific maturity.
I want to leave you with this final provocative thought straight from the text. It asks whether our collective wisdom is actually maturing as fast as our machinery. Are we building a scientific culture wise enough to deserve the tools we now hold? Data and computers have rewritten the rules, absolutely, but it is entirely up to human curiosity and responsibility to make sure those rules actually lead us toward genuine truth. Thanks so much for joining me on this explainer. Catch you next time.